Good morning, dear students. Welcome to this session on prestressed concrete, where in the last session we have talked about the advantages of prestressed concrete and the limitations of prestressed concrete. And now, in this session, we'll talk about applications of prestressed concrete. So, prestressed concrete applications I have just presented, I would like to present in terms of pictorial representations and wherever it is possible, and listed some of the applications. So let us see one by one. So this is a hollow core slab where pre-stressed concrete application, the first application. So hollow core slab panels, you can see the hollow core slab panels here, and you have to transport to the site and just join them to have slab construction. Okay, so where you can see these are the locations of pre-stress. These are the locations of pre-stressing tendons. Okay, so that's how the pre-stressing is done for the hollow core slabs. Is one such application. Then ribbed slab or waffle slab, where the network of beams uh, you can find, okay, like this. This is all hollow portion, right? Next is the double T slab or a single T slab, maybe a single T slab or a double T slab will have the pre-stressing application. And flat slabs is another application where you can see almost all the commercial complexes are built with flat slabs. And then the another application into the most promising area where the bridges, the long span bridges are possible. What you see is a 365-meter span cable stayed bridge in Florida. And twin box girder bridge is where you can see the pre-stressing cables, the box girders, pre-stressed. And so the box girders are the part of the bridge, where in Chaco Corrientes Bridge in Argentina has the longest cables stayed bridge with box girder, built with box girders. Okay. And folded plate roof is another example, another application of the pre-stressed concrete, where the roof, for the aesthetic appearance of the roof of the building, the roof is by folded plates. Okay. And space frame application of pre-stressed concrete into space frames, even space frames for aircraft service depot. Uh, if a space frame, if you say you get into a mind that it is of steel structure, but it is concrete. It is possible even with the concrete, with the pre-stressed concrete. Okay, right. And those are some of the applications that you can present in terms of pictorial representation. Now I'll just list out the different applications. The pre-stressed concrete application is into every field of civil engineering. So nuclear containment vessels are being prepared with pre-stressed concrete, and sleepers for railroads, poles, piles for building constructions, foundations, pile foundations, marine structures, applications into floating docks, offshore oil drilling platforms, and giant floating liquefied gas and oil storing vessels, and these are the marine applications, the large capacity liquid retaining structures, and tall towers to support restaurants, observation decks, radio and television facilities, where you have an example of 211 meters Stuttgart Tower is being, the application of this tall towers. The world's tallest self-supporting structure, which is a 553 meters tall, which is CN Tower, famous CN Tower in Toronto. And as I said, during the last 50 years, prestressed concrete has been used into every aspect of the civil engineering, where buildings, transportation, marine structures, nuclear structures, environmental, and power transmissions, oil exploration. Okay, this is a worldwide scenario. Now I'll see in the Indian scenario, where some of the notable examples of pre-stressed concrete structure in India. So, Lubha Bridge, the nation's longest single span bridge, where 172-meter long pre-stressed concrete box girder type continuous bridge built across a 30-meter deep gorge of Lubha River in Assam. Gomati Aqueduct in UP is another application, where 5,500 kilometer uh, weighing pre-stressed aqueduct is being built with the pre-stressed concrete. Then ball tank for the Department of Atomic Energy, which is having a 4 million liter capacity, is being built. Then Boeing hangar at Santa Cruz Airport, a roof consisting of shells having edge beams with 45.73 meters span. Then Ganga Bridge at Patna, the longest pre-stressed concrete bridge in the world, has a total length of 5.5 kilometer roughly, consisting of spans of 121.65 meter long. Then silos at Bakranangal, 312 meters long, for storage of fertilizers. Then Juari Bridge at Goa, which has 807-meter long, comprising of pre-stressed concrete cantilever box girders. Okay, so this is what no, the some of the applications in pre-stressed concrete, where in India also. Okay, so now let us go into the, the real contents of what exactly that how pre-stressed concrete is being prepared. Okay, uh, what are all the materials required? So, with the earlier discussion of introductory content, you will be knowing that the two major materials required are high strength concrete and high strength steel. So how you prepare a high strength concrete? Now let us see. Before we go to the high strength concrete preparation and requirements of materials, let me introduce the constituents of concrete. So concrete is a composite material consisting of coarse aggregates, fine aggregates, and binder. It's well known to you from the concrete technology subject where you have studied. Okay, so that is called hydrated cement. Binder in the sense hydrated cement. Okay, so the following figure show a petrographic section of concrete, and the you can see the aggregates in the picture. This is the aggregate, where surrounding that aggregate is a matrix. What we call is a matrix. Matrix consists of sand, hydrated cement, and voids. Okay, tiny voids. Okay, so that is the filling material between the space created by the aggregates. Okay, so the space created by these aggregates is being filled with the matrix. Okay, right. Let's go to aggregates part. What does aggregates mean, and how does you require the different properties of? So coarse aggregates are generally from rocks and crust stones. And if you want lightweight concrete, you can use slag, shale, fly ash, or clay. Okay, the aggregate made from these synthetic materials and will make the concrete lightweight. The sand from the riverbeds or quarries. You can say quarry sand or the robust sand. The other name of it is called robust sand. So that is what is fine aggregate. Uh, the fine aggregate along with the hydrated cement paste fill the space between the coarse aggregate, which is called matrix. Okay. The important properties of aggregates required for a good concrete is shape and texture, size gradation, moisture content, specific gravity, unit weight, durability, and absence of deleterious materials. Okay, so the requirement of size of the aggregate is presented here. So you see nominal maximum coarse aggregate size is limited by the lowest of the following quantities. So it shall be either 1/4 the times of minimum thickness of the member. Second one, spacing between the tendons minus 5 mm or 40 mm. So least of the three. For example, if I take uh, 200 mm thick member, so by 4 is like 50 mm, 1/4. And say for example, I have two tendons at distance of 40 mm. Okay, so the finally it comes around 40 minus 5, so 35 mm. And the last one is 40. So least of the three will come to 35 mm. So you have to take nominal maximum coarse aggregate size as 35. It can't go beyond 35 mm. And you have to avoid these materials like deleterious substances like clay lumps, uh, wood pieces, any coal, silt, rock dust, and also organic material. Okay, so these things shall not present in the aggregates. Okay, and the requirements of aggregate is covered in 5.3 of IS 1343 2012, which is the latest version of the code available. So just go through this code for all these requirements. I'll just present that to you. I have a copy of the code. So 5.3, section 5.3 of the code. We'll go to that. So you see that 5.3 is aggregates. Okay. So this 5 point, all the aggregates shall comply with the requirements of IS 383, means the code for aggregates is IS 383. And 5.3.1 and 5.3.2 is of size of aggregates. And okay, uh, the here it says, see, the nominal maximum shall be 5 mm less than the spacing between the tendons, sheathings, likewise. So it gave the nominal max should be as large as possible within the limit specified, but in no case greater than 1/4 of minimum thickness of the member, provided that the concrete can be placed without difficulty. Roughly for most work, 20 aggregate is suitable. Okay, so 5.3 specifies the requirements of aggregate. Okay, so this is whatever I have presented in terms of the presentation is available in IS 1343 2012. Class 5.3 will give you about the all other guidelines which are in IS 383 are adopted as it is. Okay, so heavyweight aggregates may also be used provided the engineer in charge is satisfied with the data on the properties of concrete made with them. Okay, so this is how it goes. So for most of the works, 20 aggregate is suitable, it's said. So as anything other than this, you have to go with the least dimension of the three values. Okay, so this is how the aggregates requirements are being mentioned. Okay, right. Right, we'll talk about the other constituents materials in the further sessions. Okay, right. Thank you.